All right, so back to the next page. We're talking about our 3 decay particles, giving their mass, charge, and describing the appropriate shielding. This is Unit 3, and this is talking about nuclear decay reactions, where the nucleus of an atom is changing. So our symbols, alpha is this fish-looking thing, most people call it. Beta is this bee-looking, and gamma is fish floating upside down, I guess. If I write the alpha particle out, I would write it 4 to He plus 2. So if you think that's a mass number of 4, a atomic number of 2, so 2 protons, 4 nuclei, 4 nucleons, 2 protons and 2 neutrons. Helium plus 2, that means those 2 protons are not balanced with anything. This is just a helium nucleus. If I look at its mass is 4. Its charge, let's just write charge, is plus 2. And any appropriate shielding, we just need paper to shield it. It's very low penetration, lower energy of all of our decay particles. The next one is a beta particle, and a beta particle is a 0, -1 e. It's actually an electron, so no mass, particularly speaking, very low mass actually, and a charge of -1. This is usually actually accompanied by another particle called an antineutrino, but for now we will just stick with our electron. It has a mass that's much less than 1, and it has a charge of -1. If we wanted to shield from this, we would need aluminum, about 6 millimeters. And this is sort of our middle energy particle. The last one, a gamma. A gamma is actually a particle that we call photon, and it has no mass, and it has no charge. Photons are the base particle of light. So the gamma radiation we talk about in nuclear decay and the gamma radiation we talk about in the electromagnetic spectrum are the same thing. To block against this, we really need lead, thick concrete, something like that. And this is our really high energy. So for the rest of this, we're going through the decay equations. We always start by writing them in this format like we wrote the helium. So this is uranium-238. 238 would be its mass number. 238, 92, U. And it's going to go through nuclear decay. That means out of those 238 particles, we're going to let go of 4. And out of the 92 of those particles that were protons, we're going to let go of 2. So we need 238 minus 4. 92 minus 2. And now you need to get out your periodic table, and you're going to have to look it up. The atomic number of 90 goes with thorium. All right, so the next one would be NP, neptunium, neptunium-240. So same thing, alpha decay, you have to look up on your periodic table, find neptunium is atomic number 93. Just forgot the plus up there. So it too, it's alpha decay, so we're always, an alpha particle is always this 4,2 He plus 2. So 240 minus 4, 236, 93, excuse me, minus 2, 91. 91 is protactinium, which is Pa. This is what we call the daughter nuclei, this thing that is made. So the daughter nuclei for, oops, I wrote N. There we go. Daughter nuclei for neptunium is protactinium. Daughter nuclei for this uranium is thorium. For the next one, we have lead-210, and lead has an atomic number of 82. This time we're going to go through beta decay. So for beta decay, we are going to have an electron come out over here. So 210 minus 0, still 210. 82 minus negative 1. So 82 minus negative 1 is the same as 82 plus 1, 83. And if we look for periodic table for 83, we'll find that's bismuth. And let's see, last one here, calcium 42. Calcium 42, and its atomic number is 20. Negative beta decay. So 42 minus 0, still 42. 20 minus negative 1 is 21, and that's scandium. So those are our decay equations. We don't have to write one for gamma. Gamma does not transmute. It does not create a daughter nuclei that's different from the parent. It stays the same. So why do some nuclei decay and others do not? Stable nuclei where the mass and energy are balanced equals no decay. So unstable nuclei decay. They do this spontaneously. A couple more terms for nuclear decay. Fission and fusion. These are not spontaneous. They have to cause outside reactions. So, for example, fission is when we take a big nuclei and we split it into smaller nuclei. So we're breaking up the nucleus. Fusion is when we take smaller nuclei and we put them together and make a big nuclei, so we are going to fuse a nucleus, and that's what our sun does. All right, so here's a half-life graph, and you need to be able to recognize a half-life graph. It's always going to follow one of these curves.
Good morning, Brexwell. If you happen to be a student with an overdue book, this is the perfect time to